So hello everyone, my name is Peter Bachfalushi. I'm with ITM Instruments and I'm a technical sales specialist out of Calgary, Alberta. Thanks for joining us on this webinar. Today's topic is utilizing ultrasound and vibration for bearing health assessment with SDT ultrasound. We kindly ask that you mute your microphones for the duration of the presentation. Our presentation will last between 40 and 45 minutes, and then we'll have time at the end for some questions. We encourage you to ask questions at any time in the chat box, and then we'll get to them at the end in the question and answer period. ITM Instruments has been working closely with SDT Ultrasound for many years. We pride ourselves in being a leading distributor of their products, and we dedicate ourselves to offering product expertise, service, and competitive pricing. Let's get started with today's webinar. It's presented by Gilles Lantier. Gilles is the district manager for SDT Ultrasound. He's in Atlantic Canada and Quebec. He has a long background in vibration analysis with IRD mechanalysis, NTech IRD, Rockwell Automation, GE Bentley, Nevada. Gilles is a level 3 vibration analyst and a level 2 ultrasound specialist. He's taught on vibration analysis as well as ultrasound in Canada and the US for the last 25 years. Gilles, we're ready for you. Please take it away.
Hello, everybody. Today we'll be talking about ultrasound and vibration in our instrumentation. It's your first page, Utilizing Ultrasound and Vibration for Bearing Health Assessment. And we're going to do basically mechanical inspection with vibration ultrasound. So I'm hoping that the audience has a bit of mechanical inspection knowledge as well as a bit of vibration knowledge, because it does require to understand what I'm about to go through. First of all, that's me without a beard. And there's one of our instruments on a electric motor. That's a 340, and you can see the fellow is wearing headphones. They're Bluetooth headphones in this particular situation, because we listen to our bearings ourselves with ultrasound. We're going to first start with what we call mechanalysis, which uses mechanical analysis. SDT instrumentation uses ultrasound and vibration to diagnose the variety of faults. In this presentation, we will demonstrate the use of our instrumentation to diagnose a variety of mechanical problems. 1. Unbalance using vibration. 2. Looseness using ultrasound and vibration. 3. Bearings using ultrasound and vibration. 4. Cavitation, ultrasound and vibration. 5. Gear defects using ultrasound and vibration. So we have 5 topics we'll be seeing, case histories and how they work and so on and so forth. First, before I start this, I'm going to give you a little refresher on the basics of signal analysis. The first thing you have to know about signal analysis is what a time waveform is. I suppose everybody knows this is a sine wave, a repeating sine wave, and one cycle would end over here, so on and so forth. The time waveform is simply a straight shot display of in other words, a plot of vibration or ultrasound amplitude versus time. The time waveform displays the result of one complete oscillation of one cycle of vibration generated by one complete version of unbalance. Now, horizontal axis in time. So this over here is time. Then here you have amplitude. Okay, as far as that goes, I hope everybody can follow that. We have units of measure in vibration and ultrasound. We'll start with the most simple one. Displacement is measured in mils, peak to peak. It measures the frequency of 0 to 10 hertz or 0 to 600 CPM. CPM is simply associated to RPM, so 60 times 10 is equal to 600. It's used for low speed applications like miles. Then velocity, which is the main use in vibration as a severity indicator, we use it between 600 to 120,000 CPM or 10 to 2 kilohertz. Then we have acceleration, and that unit measure is G's, and it uses anything above 120. So low frequency, mid range, high frequency. And finally, ultrasound. Ultrasound is very high frequency. As you can see, this is not even close to being 40 kilohertz. Usually vibration stops around 20 kilohertz. Anything above, we use ultrasound. Ultrasound energy is at 40 kilohertz. It's used to detect bearings, gear mesh, air leaks, all kinds of great stuff, which we'll be discussing today. Well, these are the 3 basic units with vibration, and we have 1 unit in ultrasound. It's dBs. You must have heard in the past that dBs is for sound, like a dBA. Like you can talk about a flute, let's say 75 dB, and something else would be a higher dB. You can distinguish between the amplitude by seeing how many dBs. It's the same for all. Sound, we're using dBs. Oh, now this is all done as a practical application. It detects friction, so two pieces rubbing together, as you can see. It detects impacts. It detects turbulence. And of course, there's partial discharge, which is a part of the whole thing for electrical. So it was generated by friction, impacts, turbulence, and partial discharges with this guy here. So partial discharge is relevant because ultrasound can also be used heavily for analysis, which is not a topic today, but we do have some videos of that in the future as well. We'll be mostly concentrating on friction impacts because we're looking at is mechanical problems today. First of all, this is the PF curve I'm hoping that most people have seen. Design, installation, ultrasound, potential failure, then we get the vibration, then we get the audible noise, then we get the heat, then, well, guess what? It blows up, okay? Let us do it one more time to see exactly how this works. So the first detection you have before anything happens is ultrasound. That's the first layer of protection you have for any of your rotating assets within your mills. So first you pick it up for ultrasound, for greasing. We can hear it, the darn thing's probably busted in the younger core. This is a quick refresher of the signal. This is a bearing. This is a pickup. This is a mass and a spring. As the mass and spring goes up, if I put a pen on it, it would draw a sine wave or a time waveform, right? All our analysis today will be based on the time waveform. And if when you do the frequency is 1 over time, where I have my time here, I just do the inverse, and I use the amplitude here, I have what we call a spectrum, or an FFT, a fast Fourier transform. All the analysis done by modern instrumentation today uses a time waveform, as we can see here. This is a complex time waveform, which is decomposed into the frequencies over here, which gives us a spectrum of there. So we can get out of this all the frequencies in here with this. The thing about the FFT is a lot easier to see the content of a signal with an FFT than it is with time waveform. So a lot of our signal analysis will be done with the FFT time. All of our stuff you'll see in the next few minutes will be based on that as well. Here's the first topic we'll be talking about, unbalance. Unbalance is the most common source of unwanted vibration. Erosion and dirt are the most usual causes. Simply cleaning a fan may sometimes correct the problem. You can only diagnose unbalance using vibration. You can't use ultrasound. Unbalance is a low frequency event, and ultrasound is a high frequency event. Unbalance only occurs at 1 time the speed. Erosion it should be less than 5 to 1. What do I mean by that? I usually take a horizontal reading. I'll take a vertical reading. Both all have amplitudes. As long as my horizontal reading and my vertical reading, the amplitude between the two does not exceed 5 to 1. It's unbalanced. Anything beyond 5 to 1 can be considered mechanical looseness or resonance. Now we can see the spectrum of unbalance as being one peak at its rotating speed. You can also see here the difference in phase for unbalance to give us our 90 degrees. But I'm not going to get too much into that. That's phase analysis. I don't want to make this course more complicated than it has to be. Okay. So as I was saying, this is unbalance, 1 times RPM peak. That's how we recognize it. It only occurs on 1 times RPM, not 2 times, because on a rotating unbalanced wheel, it spins at the same speed of the wheel. That's how you diagnose unbalance, by looking at the spectrum. It's a 1 times RPM peak. We move along. The next thing we'll be discussing is looseness. Mechanical looseness is a condition that responds to other mechanical problems, and by itself is not a vibration force. In fact, there are some types of machines that are not even built bolted to the foundation, but instead sit on an electromagnetic pad, or springs, or anything like that. Like, for example, suppose I go on a roof. You know, a lot of people that are mechanical inclined, they know down the roof there's fans for ventilation. Most of the time, fans are on springs. The springs are used to isolate the vibration to the fan, and that's put it to the roof. But by doing that, the actual machine itself will vibrate it more. So the tolerance levels for misalignment and balance on these things will be higher because they're on springs. That should be clear. And typically it produces rotational speed harmonics. Harmonics are multiples of a frequency. Or our frequency is going to be the fundamental frequency, and our fundamental frequency is whenever I have a multiple of the rotation speed, 1 times, 2 times, 3 times, 4 times, 1 times, 2 times, 3 times, 4 times. You can think it as being something loose. Another thing you can refer to is a time waveform. See a little thing over here? Oh, it's made, it's not a perfect round circle. That's an impulsion, that's an impact. I'm telling you this is looseness. Here also, when your time waveform almost looks like a square waveform, is another symptom of looseness itself. So whenever I have this and these things, you can pretty sure bet you have a looseness problem condition within your machinery. Looseness can also be detected with ultrasound. Ultrasound can also be used to detect looseness. Ultrasound defect detects friction, impacts, and turbulence, fit, what we saw a few moments ago. Therefore, when two machine components are loose and impact each other, we can hear it and record it. Here again, we got the impacting and time waveform at the bottom, bing, 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 and we have the spectrum over here showing us harmonics. So whether you have vibration or you have ultrasound, both can detect looseness conditions. So, but ultrasound, it would be a bit better to detect fit problems within bearings, because you see these harmonics up here, okay? And also occur at higher frequency. So depending on the situation, you might use both just to make sure of what the diagnosis would be. So we can use both technologies to do the same thing, but it gives you more confidence by using both. Now, since we're going to do bearings, let's know what's inside a bearing. First thing, you have an inner race. You have a right here, inner ring. You have an outer race. You have the outer ring. You have the ball itself, and you have the cage. All these components have frequencies we can detect in vibration ultrasound. The BPFI, ball pass frequency inner race. BPFO, ball pass frequency outer race. The BSF, the ball spin frequency, and the FDF, the fundamental transfer, which is called the cage. So all of these components of the bearing can be actually detected within a rolling element bearing. So in bearings, there's 4 stages of failures. In vibration training, always talks about the 4 stages of failure. 1, the friction goes up. If the friction goes up, the ultrasound goes up. High frequency random impacts, therefore, just start to be a bit of looseness. Then the bearing defect was before. Then when there's no more geometry left within the rolling element bearing because it's been damaged beyond any mathematical concept, all you need is a random high frequency noise. It's a bunch of jumbling and noise. You can actually hear the bearing at this point. In ultrasound, it picks up the early stages of failure. Starts to fade off, but the bearing begins to, the bearing defect frequency begins to appear. Ultrasound overlaps with vibration, so the combination is complementary. That's why in most predictive maintenance programs, you have both the ultrasound and the vibration to help you diagnose problems. This is an example of the 4 stages of failure. First thing that happens, initial indications of bearing failure at ultrasonic frequencies, 1.2 million to 3.6 million cycles per minute, or 20 to 30 kilohertz, depending on your like times 60 kind of a deal, right? So there, the ultrasound started to happen, nothing's whole. There you go. You can probably just grease the bearing a bit here, you bring everything down. As it gets worse, the resistance of bearing and the natural frequency is coming up and down in between 30 and 30. In other words, when you start having a small indentation, a small crack on your rolling element, the balls will start hitting it. It's like a little hammer hitting, ding, 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 so on and so forth, which will make the bearing ring as its natural frequency. And it will be surrounded by these 2 little peaks, which we call sidebands. And at this point, the ultrasound is going up because it's impacting more and more, right? Versus there, high frequency, lubrication, then it's actually a defect starting to appear, the ultrasound goes up. As it gets worse, you're going to start seeing the bearing defect frequencies appear. The BPFO, the BPF5, and so on and so forth, and bearing natural frequency. The defect frequencies of the bearing appear as where it progresses, much more harmonics appear, and the number of sidebands increase around natural frequency of the bearing components. The ultrasound is increasing where it's now visible and can extend to the periphery of the bearing, especially if the well-defined sidebands component frequency. You change the bearing now. Once you see this stuff, don't argue with it, just change it, okay? I've done it in thousands of bearings. When you see this in velocity bearings, it's toast. Just change the darn thing. Besides, at this point, you can probably hear it, you can probably touch it, and you don't need an instrumentation. The whole point is not to get here, or to measure until you get here so you can plan a shutdown of your equipment so it doesn't cost you a fortune when you plan a shutdown. Finally, when this is done, all there's left, there's no more geometry left, so there's a bunch of noise. This all comes down as random noise. The ultrasound actually goes down because there's no high frequency left till just before it blows up, it goes shooting back up. So those are the 4 stages of a bearing. Okay, this happens thousands of bearings every day in the world. These are our approximation frequencies. Suppose you don't have a bearing database, you can say, number of balls divided by 2 times RPM times 1 minus ratio, and ratio is divided by d close to here, and close to 0. Okay, so you can do the math yourself. It's very simple math to get your outer race, inner race, ball spin, and gauge frequency. But it's not that accurate, but that'll give you something to work with. But if you really want to be accurate, you use these wonderful formulas. We have all kinds of parameters within them to give you the outer race, inner race, ball, and cage. Fortunately for us, we don't have to do this anymore because the bearing manufacturers, whether it's SKF, NTN, FAG, you name them, they give us their bearing defect frequencies because they've already figured out this wonderful formulas. So we can insert that in a software package. Before I go further, I'd like to make sure that you guys know there's 2 ways to detect a bearing. One is with an accelerometer for vibration. 2 is with ultrasound over here. Then these 2 pickups over here, okay, this is a parabolic dish, and this is a flex sensor with a microphone, can also pick up defective bearings. Some applications are difficult to reach with the contacts, but are easy to work. This is a parabolic. This is like a 20 meters. So suppose you have a conveyor belt, you can't reach or nothing like that. You point at it, sounds good, sounds good, sounds good, sounds like shit. Excuse my language. Okay, that bearing probably has a problem. You're scheduled to read. So you can easily go around your conveyor belt to find all your defective bearings very quickly for shutdown purposes. Sometimes airborne is all you need, right? Now, inside our software, we simply pick a pickup, which is SDT we call it. Often we take the measurement. Acquisition time for this is 25 seconds. I say it's an SKF N204. I press this little button here, brings me to the bell ring selector. Is it by SKF? Is it by Koyo? Is it by NTN? Is it by SNR? So on and so forth. You pick the right one, which gives us the multipliers for the bearing here. So I take this speed here, 37, multiply by this number here. It gives me the inner race. Multiply this number here, it gives me the outer race. So on and so forth. Once this is all programmed inside software, you can, when you make your spectrum up here, remember, we have impacts and stuff like that. The frequencies, when your bearing selector is here, you choose in this particular case PPFI, it will actually put lines on your graphical display. If those lines happen to land on the piece you got there, you know it's an inner race, an outer race, a cage, or whatever. So it makes the diagnosis very simple for a problem for a bearing. And also, this is on the spectrum. You can also see it on the time waveform. So you get additional confidence when you call a bearing. You can actually see the pattern of deterioration. And this is with ultrasound, by the way. Okay, so this is an ultrasound. You can see it here. This is all dBs as well. All right. This is what we use in UAS3 to diagnose bearing problems. We move along. This is a structure-borne problem. This is an airborne problem. I'll make you listen to this. I'll switch over my sound. You must have heard both the structure-borne and airborne. They sound slightly different, but when your ear is trained, you can basically know which one is which. And if you can't reach something that's too far, you just use your parabolic dish or the flex sensor. You can find out if your bearing is in trouble or not. Now, there's another bearing. This must be a bit more obvious. Okay, now one thing that is in ultrasound, which is much better than vibration, is for slow speed application for rolling element bearings. Imagine this. Okay, it's considered to be difficult, but many in the vibration will take slow speed bearings for problems. It requires special treatment in terms of sensor use and acquisition time. Friction, early stage defects, even defects will still be detectable ultrasonic. In other words, vibration works with the idea of force is equal to mass times acceleration. The faster it goes, the more force you have, therefore the frequencies will appear a lot clearer. But if you are going very slow, there's very little centrifugal force, therefore you cannot detect it very well by vibration. There's not enough amplitude for it to actually come out of the grass. Whereas ultrasound is specifically made for that because our sensor is tuned to the frequency we use. Our sensor's natural frequency is and we're exactly at that frequency. And so anything at high frequency, the very beginning of a bearing, deterioration will easily detect it. And something that's going very slow, we'll be able to amplify and see it. For example, here is a hoist bearing. This thing travels for 30 seconds, right, from start to stop. In vibration, it takes at least a couple of minutes to take something that goes this slow. You don't have a couple of minutes, you have 30 seconds. So one of the only ways you can detect this is with ultrasound. Example, here's a time waveform. You can see the bearing condition here, and I'll play this sound right here. So it's very easy to detect a slow speed bearing. Okay. So this thing was going at 14 RPM, and the inner race was at 173 RPM. I just told you why, because we actually boost the signal because the natural frequency of our sensor and what we're looking at is tuned. We're the only company, as far as I know, has the tuned system. All right. So we can basically detect these low frequency events. I have a lot more examples coming in. Here's another one, a conveyor bearing at 238 RPM. It's still pretty slow as far as I'm concerned. Here's a pick. On top. This little thingamajiggy on top there, that gives us our natural frequency of 40 kilohertz. Okay, and there's the sensor itself. Right, and then the cable going to the instrumentation. Because of this, we'll boost the signal mechanical amplifier. That's what this thing is, a mechanical amplifier. We'll move on. With this, my friend, works in his company, was able to get the defect frequencies, which you see here, overlay the cursors on top of the impacts, and deduce from the frequencies. This was an auto raise problem with the bearing, and this thing was 230 RPM. Before you can see nothing in vibration at all, even in demodulation, which is what vibration uses to look for raise frequency. And he was only able to see it with ultrasound. A lot of cases are like that. I'll move along. That can do both. The vigilant mobility and the SDT 340 both do vibration analysis and ultrasound analysis, spectral analysis, and time waveform analysis. These are two complete packages for a predictive maintenance program. Here's some case studies ensuring the defective bearing made it to the shop. That's one of the things, like for example, in paper mills, yeah, we know we have a problem, we can't stop. Production is always the boss for anything. Okay, so we have to have a way of monitoring it. If it gets too bad, we'll have no choice, but we want to make sure we get a shutdown. So how do we monitor this? We have the vigilance system, which has 8 inputs of ultrasound or vibration. Also has attack input and other types of inputs for other types of things. It also has a mod bus, so if you want to bring it to a PLC and so on and so forth. This is the one that's permanently installed. There's also a mobility one, which we see over here, which has a built-in Wi-Fi and also a built-in cellular connection. So if you want to actually leave this next to some machine remotely, as long as it says on your sofa and monitor the thing over the weekend or whatever you want to do. And of course, there's an SDT for 340, which monitors directly online with the stuff. These are diagnostic instruments at SDT, which we manufacture. Here's a section of a paper mill, the operator side. These are 2 presses. For anybody that knows what a paper mill is, these they move back and up and down. to determine the thickness of the paper, all right? Now, when they were taking this thing apart, unfortunately for them, one of the hydraulic motors kind of fell, so the two brand new rolls which had recovered, okay, they got kind of impacted each other. So, oh shoot, what would we do now? So they took their old rolls and put it back in place. The old rolls had a problem, but it was the guy, and these were pretty much, you know, they had a bit of impact. They didn't want to take a chance. So we installed, this is the drive section, by the way, in case you can see, that's a big long drive shaft. I just wanted to tell as well. We basically mounted both sides of the bearings for them with our vigilance system. The vigilance system gave us this. See all the impact? Click, 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 click. And every one of these is a measurement. So we're going back and forth in time and history and so forth, okay? The vigilance system is a self-contained environment. You don't need external software. The software is within the vigilance itself. All you got to do is log into his webpage, and you have every functionality and any ultrasound or vibration system will have. You have phase analysis, time waveforms, scatter pools, and you name it, it does it. So at the end of the day, you can just put this on and look at it and take it day by day and monitor it as it goes along. Of course, we have the BPFO up there. Then we have, by the way, this thing's going about 150 RPM. And of course, here's the velocity, okay?
Joe, can you restart that slide? I didn't hear you at the beginning.
Which slide? This one?
Yes, from the beginning, the first section you were talking about.
Oh, here?
Well, the third phase. Yeah.
Right here?
Please.
Well, all this is ultrasound here. It's just pointing out what unit of measure we're using. And here it said that the ball path, the outer race defect that appears in ultrasound, okay? And you see amplitude and so on and so forth. Then I showed up, this is vibration and demodulation, which we do also on the version. It does both. Okay, so you can see the BPFO as well. And then I showed you the vibration and velocity, inches per second RMS here, where the bearing is not very present so far. As we go along, here's the ultrasound sort of top roll. I have it sound here, so I'll play that. You can't really hear nothing in this particular situation. Like, there's a little something. But when you look at the spectrum, it clearly comes up. So sometimes you do need the spectral analysis just to make sure it is. It's not clear impacts all the time. Spectral analysis is very important for this. Again, it's the BPFO and its harmonics showing up. This is using UASA 3 and the 3/4. Then again, the other side, we have again the BPFO. It shows you with the cursor, tells you delta F, tells you what frequency it's on, and the multiple harmonics of the defect frequency. Then we can look at the impact in the time waveform. It did a better job when you zoomed into it. You can actually see the impact inside of it. Then with the vigilant, you can see the impacting, but you'd have to zoom in a bit more to see the impacting than we did with all the UAS3. Then we have, again, the demodulation, ultrasound demodulation, which is basically our ultrasound signal again. Nice and clear, so it's getting worse. Then we have it also in vibration. So we can do both. You can actually have fully, if you want to monitor the heck out of stuff, you can use this, so you can do everything you want. Then, hey, now we're in velocity, right? Yeah, the BPFO is now appearing in velocity. That's when you know, oh, now I gotta do something. It's in velocity. I have to change the thing. And that's what tells us. We don't really care about the amplitude over here. We care about the content of the defect. And the content shows up, here's my defect frequencies, here's the velocity. That is my trigger point to stop the machine. I have no more choice. That's how we do things. Here's another little sound for you. That one was clear. You could hear the impacting, was clear as that bell. You don't have to ask yourself a question. You show that to anybody, even somebody who's not familiar with vibration or ultrasound. This is what your bearing's doing. It's impacting. You get it off the bat. You don't have to be. Then you look at the spectrum, again, boom, boom, look at this well-defined spectrum with all the repeating impacts within it. Ultrasound as well. Another one, just to give some more meat to the juice, here's 1197 again, it's still a BPFO, you can see it right here, your bearings right over here, and so on and so forth. Again, the impact and clears a bell and ultrasound, boom, 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 there's the bearing. Then on the vigilant, we have trending of sound and the vibration simultaneously, so you can track both at the same time in a lifetime environment. Because a vigilant is a lifetime machine, so you can take an instantaneous reading, and you can have alarms. You can stop the machine, all kinds of stuff, because it's a Modbus, because of a PLC, operator, or whatever you want to do. Again, here's the vibration log with the bearing. Again, on the vigilant, and of course the ultrasound has the same thing. So with the vigilant, you can do monitoring of the wazoo, whether you want to use ultrasound or vibration. You have all this stuff here, and the ultrasound gives you time. Oh, you have to grease it now. Your vibration will give you that, but not as clear as indicator as ultrasound. So on top of telling you to your problem with bearing, put a bit of grease in, you'll make it last longer. You can't do that for you. Now, what about gearboxes? What can go wrong in a gearbox that will generate friction, turbulence, or impact? A whole bunch of stuff. Don't forget the drive of the gearbox, the coupling or belts. So one thing I'm not mentioning today, but it's one of the rare technologies to listen to your coupling with the flex sensor or any other air microphone type of sensor, where you can actually see the condition of your coupling. Vibration cannot do that. I have a whole presentation on that, but I will save that for a later time. What could go wrong with gearboxes? Worn teeth, misaligned gears, chipped or broken teeth, eccentric gears produce a series of high spots, poorly greased bearings, poorly oil-fed bearings, high gear tooth friction, misaligned pulley or couplings or input-output shafts of the gearbox, cavitating fuel pump, block or constricted oil filter. So all kinds of stuff can happen to a gearbox. Or to take readings. That's one thing that always, where do I put my pickup on this wonderful thing? You need to keep in mind specific acoustic impedance. Now, for the people who don't know what the hell that means, when a sound wave traveling in one medium reaches a boundary with another, two pieces of metal, some portion of the sound wave will be reflected. So the more interfaces you have between you and the pickup, more reflection will occur, therefore the smaller the amplitude. Ideally, you put your pickup as close to the bearing as possible. You need a reading on each bearing of the housing if possible. My speed of going to terminals. As you've seen so far, I need the speed to calculate my inner race, my outer race, and all my defect frequencies in any case. Here's another. You can see, you can't really see nothing here. Okay, this looks pretty okay, whatever. If I listen to it now, that didn't sound too bad, did it? Right? But if I look at the spectrum, oh, look at that. 1, 2, 3. These are gear mesh frequencies. 1 times gear mesh, 2 times gear mesh, 3 times gear mesh, 4 times. Gear mesh is simply a number of T times RPM, and these are multiples of those frequencies. Okay. Then we took apart a wonderful gearbox, and we found this tooth damage with ultrasound, just because of the gear mesh stuff. I'm pretty sure most of you know that ultrasound can do all this stuff. It's something we've been looking at for a while. We're trying to show people how it can be utilized. Now, a wind turbine gearbox. Here's your main bearing. This goes at 16 RPM or something like that. Then you have a planetary gearing. Planetary gearing because a generator at the end of this, that's going to be turned fast enough so it can hook up to OPG or Hydro-Quebec or Manitoba Hydro, whatever, Saskatchewan. Because it's 60 hertz is I think in Canada, so that's 3,600 RPM. So we were bringing this up to a certain speed so we can actually bring it to bring generator power to the rest of the network. Here you can see in the time, this again on a vigilant, the time waveform impacting is starting to occur, bing, bing, bing. This is the time slots we're locking in. Here the spectrum doesn't show us too much so far. As we go on up, the high-speed gear goes at this speed, number of teeth 91, okay? Times RPM, just 675. So this the RPM we're looking for. Then we go, oh, we're going to zoom into this thing. And look at offset. We take it apart, look at the damage on the gear. Again, with ultrasound. The next thing we're going to examine, since we did a lot of gearing, we did a lot of bearings, and we did some unbalance, and we did some looseness, we're going to look at pumps for a little bit. What can go wrong with a pump? Bearings, coupling alignment, seals, cavitation, mechanical looseness, suction, and discharge valves. Boom. These are all things that can go wrong with a pump. Now, cavitation can do this to your impellers. You have never seen this before. Some of you have seen it many times. But cavitation basically destroys your impeller. It eats away at the metal. It's a big killer, often caused by operators. Detect early stage long before you try and get it before you have to take the impeller out like that. Is it caused by the implosion of vapor bubbles in the liquid? I'll just sound through the random bulb. I'll give you a sound of that as well. Also have a little video that's going to come up here. Inspecting the pump, but not the valves. One thing, okay, we have a pump right there. It's got problems. What about all the valves surrounding the pump? If the valves ain't working properly, you can make a cavitation also occur. And a lot of times you might change something in process, or the paper machine's going faster, or whatever on your process. Something has to change with the pumps. All kinds of stuff. Turn on and so on and so forth. You don't know if it's working or not. When I just the valves can have a major effects on the pump. Check also for passing non-return valves, making standby pump turn backwards. I'm going to present you a little presentation on cavitation here.
Metal erosion is a costly problem. It attacks pumps, valves, piping, and other expensive equipment. No matter what type of liquid is being used, there's always the risk of damage from flashing and cavitation. Wherever there's a restriction in flow, the decrease in pressure can cause a fluid to reach its vapor point. Flashing occurs when the fluid vaporizes and remains a vapor. Metal erosion caused by flashing appears smooth and shiny. Cavitation occurs when the fluid vaporizes, then returns to a liquid state as the pressure increases downline. The metal damage caused by cavitation is rough and irregular due to pitting of the surface. Cavitation is a major source of damage in control valves and other components. Cavitation occurs as a liquid passes through a restriction, such as a valve. The restriction causes the liquid's velocity to increase and its pressure to decrease. The point of maximum velocity and minimum pressure is called the vena contracta. Vapor bubbles form in the liquid when the pressure falls to near the level of the liquid's vapor pressure. When the pressure recovers downstream, vapor bubbles implode and return to liquid form. After the initial bubble formation and collapse, the bubble may reform and collapse a second time. Liquid microjets form when the recovering pressure makes an indentation in a bubble. Then the microjet bursts through the bubble. These implosions can also cause local pressure waves of up to 100,000 pounds per square inch. The combination of pressure waves and microjets cause severe damage to the valve plug, seat, and body when they're located near the material surface. Cavitation can also cause unacceptable noise and vibration that reduce efficiency or lead to loss of process control. Even though cavitation occurs, it doesn't always cause damage. The extent of cavitation damage is affected by the following factors. The intensity of the cavitation. Greater drops in pressure increase the potential for damage. The materials used in the construction of the area where the cavitation occurs. Hardened materials reduce damage. The length of exposure to cavitation. The more frequently cavitation occurs in an area, the more likely it is to sustain damage. Valve size. Increasing the valve size is to make the effects of cavitation worse. The design of the valve and trim in the area of cavitation. High recovery ball and butterfly valves are more susceptible to cavitation damage. if there is leakage occurring when a valve is closed. Fluid leakage moves fluid from a high-pressure area to a low-pressure area, which results in cavitation and potential damage. Cavitation damage can be reduced by altering or accommodating factors. Cavitation damage can often be reduced or prevented by using the proper components.
As you can see from this short video, that cavitation can not only have problems on your impeller, but on your valves. So with ultrasound, you can listen to all your valves as well, find out if they're cavitating and if there's a process-oriented problem, which will save you all kinds of money, and that's the point of doing any of this predictive maintenance problems. Okay, we move along. Here's a nacelle for a wind turbine. Inside there, you have a main bearing, a gearbox, a generator, and so on and so forth. A control box, and revolving stuff. We can see the amplitude and dB microvolts across a whole machine. Here, as a system overview, we can see the main bearing, the gearbox, and so on and so forth, the generator, and so on. You can see where it's high by the color scheme and alarm sets. We can see inside this planetary bearing impacting occurring within the, if you can see here, therefore this is ultrasound. Picked it up ultrasound, and you can see the impacting, which I'll make you listen to me there in a moment. Now that was pretty clear indication there's something wrong with this bearing. Okay, if you can't find that one, good luck. We move along with the greasing of the main bearing. It started at 20 dB. We stop the machine. We grease it. We bring it around that. Again, with ultrasound, you can see, I'm missing a lubrication. I turn the machine up. I grease it. It's back to a normal state. Now, again, with further analysis, we need the speed, and we have the inner race and outer race and all them with the whole stuff to get us the bearing defect frequencies. And finally, we get our impacts in our time waveform analysis and our spectrum and harmonics of the BPFO. This is what we can do with information. There's virtually nothing you cannot detect. High speed, low speed makes no difference. You're covered. That's what SDT can do for you. That's it. Do you have any questions?
Thank you, Jill. I think that was great. The sound was cutting out a little bit, so thanks for your patience there. I think I got a good understanding. I could hear you most of the presentation. So I do have a few questions that came in. The first question is, when is vibration more important for doing machinery analysis?
Unbalance can only be detected with vibration, right? Certain mechanical problems are necessary. You need vibration. Some mechanical problems you use ultrasound. You need a combination of both. There's no one thing that's perfect. The combination of both vibration and ultrasound they're complementary one to each other. For example, I can still, like, for a coupling, I cannot use vibration to see if the coupling is going for, not good. But if you take a flexible cover, you can listen to it. You can hear the actual impacting within the coupling. Vibration can't do that. So you use them both together, you have a full system. Because if you only use one, you're missing out on a whole bunch of stuff. Some things vibration is better at, some things ultrasound is better at. By using both, you miss nothing.
Perfect, thank you. And on the vibration side, should we take 3 axle measurements?
I think the HVAs, horizontal vertical, actually only one analysis. Because suppose you're on a machine, a motor, or anything else. You take horizontal and horizontal. If the horizontal goes up, means the vertical went up too. Okay? Now, if you want to have a really big database, go for it. Take your HVA everywhere. Usually, I take HVA, H. In other words, between the coupling, I need an actual measurement to see if there's a misalignment problem. Between the horizontal and the opposite drive end, okay, or I would not take a actual measurement because I find it pointless. So some places need more than one measurement, some other ones don't. if you want to take a lot of data from nothing, be my guest. But you don't have so much time during the day to look at all this data. Therefore, if you just limit your data acquisition to what is necessary, and once the horizontal go up, as you're taking it, you go back to the machine to do a forward analysis. It's as simple as that. Do you need it everywhere? I say no.
Good.
I never have taken it everywhere. So that's
Perfect. So that just about sums up our hour. On behalf of ITM Instruments, I'd like to thank you for attending our webinar today. We hope you found it informative and helpful. If ITM Instruments is able to assist you in any way, please visit us on itm.com. From itm.com, you'll have access to our entire list of SDT ultrasound products with descriptions and specifications, and you'll also find our contact information and how to get in touch with us with any questions that you might have. At the end of the seminar, we'll have a very short survey. We invite you to answer these questions, and it'll help us bring more topics to you. We have upcoming webinars in the next few weeks and months. Visit us regularly in the training section of itm.com for a full schedule. And don't forget, we're going to give $100 out as a itm.com gift card for the next online purchase to the winner of one of our attendees. The winner will be announced on our social media channels. Again, thanks for attending and have a great day, everyone.
Bye now.